Started. So last time we talked about physics-informed neural nets. Um, the idea of neural net that we've been building is basically some parametric representation of mathematical relationship. So and then we're interested in modeling the position x of that Spring-Stemper system as a function of time t. So that for any given time t, we can predict the position of the system, right? Predicted by the neural network over here. The idea of physics-informed neural net was nothing more than a regression, right? So we basically wanted to regress the neural network prediction x with respect to the ground truth x hat, so that the difference between the x hat and the predicted x gets minimized. And our goal is to find the optimal parameter configuration to minimize that prediction error was the one thing. But then obviously in the real world scenario, we do not have luxury for the most of the time to afford a large number of x hat to train our model, right? So in case of computer vision and medical imaging applications, there were millions of images available. So we have millions of x hats, right? And then we could train our model on that large data set. But in our case, relation or experimental results, we cannot that much of that many x hats, which is why we're introducing some secondary loss term called the physics-informed loss. The idea of physics-informed loss is excuse me. The idea of physics-informed loss is that since we do know the governing equation of the system, which for the harmonic oscillator case is mx double dot plus cx dot plus kx equals to 0, right? We know that mathematical relationship. We're going to use that relationship to define additional loss term, so that using that loss term, we can further fine tune the theta, right? So for the information that are not covered by the data loss terms. Data loss terms are some scattered points in the data space, right? And for the areas where we do not have those observations, we're going to be relying on the physics-informed loss term was kind of the idea, right? Now, for many of the governing equations that governs physics, so not necessarily just the Spring-Stemper system, but also many other physical systems will involve some kind of a derivative, right? Which is why they're called differential equations, right? At first place. So you're going to be, you're going to need to take the derivatives of some neural network model quantity x, okay, with respect to time in this case. Also, for the cases of PDE, you will also need to take the derivative of x with respect to some, some other quantities like position vectors, and so on and so forth. And then, for that kind of derivatives, saw last time the automatic differentiation, and then the pi implementation of automatic differentiation, which is called the autograd. So, operationally speaking, what you could do is to take the automatic derivatives and then compute the derivative terms, and then construct the physics-informed loss term, and then you could train your model. Last thing as a recap, we also saw that the physics-informed loss terms were evaluated at the locations called the co-location points. Those co-location points are, usually an arbitrary sampled set of points in the physical domain. So again, in our case over here for the spring mass damper system, our physical domain is only the time domain t, right? But for other little more sophisticated cases, like the ones that we're going to see today, the physics may define, maybe defined not only over time, but also, with respect to some space or position vector r. So what you ought to do is to sample some random points in that physical domain, right? And then on those randomly sampled points, you evaluate the physics-informed loss terms. And remember that for the evaluation of the physics-informed loss, you do not need the ground truth, okay? For data loss, you needed to, evaluate the x hat. You needed to have the x hat to define the loss term itself, and you needed a ground truth. But in case of physics-informed loss, there's no ground truth. Okay, you just need to take the derivative of the neural network, construct the equation, flow all the collocation points through that, neural network, evaluate the PD residual or the residual of the governing equation, and that is all you need. So what that means is, without having to worry about the cost of sampling the ground truth, right? You can have as many collocation points as you want, and then you can have to use that to refine the training of the physics-informed neural network. Okay. Yes. Questions. That is a great question. So for the sampling of the collocation point, the default setting is to just go with a uniform random sampling. Okay, so you just uniformly sample across the physical domain, and that is by default what you would need. But later we're gonna see that for some complicated physics, you may need to actually sample the collocation point more strategically, so that whenever, for example, nonlinearity happens, whenever there's some, sharp change in dynamics, or some interesting things happening in the boundaries, and so on and so forth, you may want to sample your collocation more, much denser in those locations. Whereas when the dynamics is kind of smooth and nothing interesting happens, then you can reduce the density of the sampling. Yeah, yeah. If you similar to that, we can allocate collocation points, much denser near the area where the physics is, expected to be, much more sophisticated. Whereas in the smooth areas, you can kind of sample less. So there are adaptive sampling strategies, and we're going to be, talking about that soon later in today's lecture. Other questions? Yes. Hmm? That's a great question. So if your governing equation is in the integral form and there's no way to make it a differential form, then I think you're going to have an issue. Although I cannot think of a specific example where that might be the case. So most of the time, you should be able to, convert your equation into, something that looks like that. And in fact, we're going to introduce more generic form of governing differential equations. And I think 99% of the time, you will have that kind of representation. So there's no concern there. But for whatever reason, if your governing equation happens to have integrals and things like that, then it might be actually difficult to define the physics and form laws, because numerically integral is something that is very difficult to compute. The computation of the integral itself will require some additional numerical methods like Runge-Kutta fourth order or other solvers. So in that case, I don't know, defining physics and form laws is going to be, a practical thing to do. That's a great question. All right, maybe one more question, and then we can move to the yes. Oh, the weight term applied to the data loss and the. Oh, that's a great question. So you probably noticed in my sample code that there was some number multiplied to physics and form laws. The bottom line is if you have, too big of a physics and form laws, then your model will not converge at all. So for most of the differential equations, there's a trivial solution, which is called not doing anything. So like in this case, for example, the PDE residual can be made 0 if x equals to 0. So if you don't do anything to your system, the position stays the same, no velocity, no acceleration. So all three terms are 0. Then, the PDE residual is 0. So that's a trivial solution. And when the training begins, if the physics and form loss term is too dominant compared to the data loss term, then numerically speaking, it'll try to converge to that trivial solution of not doing anything. So your neural network will simply just spit out zeros all the time and then not converge anywhere. So as a matter of fact, in the harmonic oscillator example, last time we saw that, we could fit this, vibration curve. But if you increase the weight term for the physics and form loss, what's going to happen is the neural network will be a flat line for the entire time interval. Because not doing anything, right, staying in the same position is the best way the easiest way to, at a data loss term. And then once the system, the neural network sort of converge, then you want the physics and form loss term to start to kick in. Okay. So in theory, you gotta have some small, weight applied to the physics and form loss term compared to the data loss term. But then how small is small, right? You want to have an adequate value. If it is too small, then basically there's nothing, no difference between physics and form neural network and just a regular neural network, right? Versus, like I said, if the weight value for the physics and form loss is too high, then it's not going to converge anywhere. And that is, in fact, one of the downsides of physics and physics-informed neural network. It is very difficult to train. It is very, very difficult to train, and there are a lot of hyperparameters like that. So it's going to require lots of trial and error. Okay, and if it requires lots of trial and error, it sort of defeats the purpose. I mean, the purpose of using neural network and machine learning approach is to make it a rapid approximation as opposed to like spending a lot of time in solving the the physics system in a rigorous manner. But if the training takes that long and lots of trial and error, the practicality of PIN becomes a little questionable. So we're gonna actually take a look at that later today more in detail. All right, lots of great questions. So what I would like to do today is to generalize this a little bit and then make it applicable to sorry about that. Yes. So no matter what kind of physics problem that you consider, at the end of the day, it will boil down to a homogeneous PDE, where we have the partial derivative of the physical quantity. So this is the quantity that's evolving over time, and that rate of evolution is defined by some differential operator n. Okay, that takes the physical quantity u and spit out some other function. So an operator is kind of function of functions. An operator takes a function as an input and then will spit out another function as an output. So d dt, the first derivative, you can consider it as that as an operator. DDT, what it does is to take a function as an input, and then we'll spit out the first derivative, which is another function, right, as an output. So we assume that there is some relationship given in this manner. We also, in terms of the terminology, we also consider that the variable x is a position vector in the physical domain omega. So omega is your physical domain. If it is a fluid dynamics problem, most of the time, the shape of omega is kind of a rectangular box, right? Or if you're considering finite element analysis of some structural component, then omega is basically the 3D volume defined by a CAD model, right? And of course, that omega is embedded in RD. So that's the D-dimensional Euclidean space. So a lot of times, we consider 3D or 2D, right? So D is either 2 or 3. We'll see a one-dimensional heat equation soon. So in that case, D equals to 1. And then also the time variable t is another very important variable, because obviously we're talking about a time evolution of a physical quantity. And then we consider that the time t is defined in the interval 0 and t, which is a subset inside of a real line. So given that kind of a PDE, we call U of T solution function. Now our goal is to find U, okay, satisfies this relation, right? Is what we would like to do. From now on, we're going to be using subscript annotation to, the sake of brevity. So use of T is typically in the PD literature denotes partial U, partial T, the time derivative of the, the solution function U as a shorthand. Like I mentioned, N is a nonlinear operator parameterized by some, physical parameter lambda. So lambda, for example, can be things like the stiffness matrix of, your solid system, or it could be the Reynolds number defining the fluid flow. Any physical parameter that governs the physics is represented as lambda, and then operator n is factorized by those physical quantities, so that the rate of change is defined by those physical quantities as well. And then finally, omega, like I said, is the physical domain whose boundary is denoted as partial omega. So here's a very simple example of a physics problem that will follow this form, right? So linear convection diffusion equation is an equation that describes, two things, a diffusion where, quantities like temperature will start from, one kind of, concentrated location, and then it'll start to diffuse. And then, the heat is going to be delivered to the surroundings, right? Convection is, convection is a, phenomena where instead of heat sort of diffuse and, getting delivered to the surrounding, the material itself kind of move around. So when you, for example, boil water, right, the water will kind of, start to flow, right? And because of that movement of the water particles, the heat will, move to, from one location to the other location. So that is, what's called a convection. So the convection diffusion equation over here, equation describing those two phenomena acting together. So again, when you boil, then the heat will diffuse, right? But in the meantime, the material itself will also move, right? And in that way, the convection phenomena and the diffusion phenomena happens together. And mathematically speaking, the convection diffusion equation looks like this. So we have the partial derivative of U, okay? So U is the physical quantity that is either diffused or convected. So temperature is an excellent example, right? So partial U, partial T, the rate of change of that physical quantity is defined as, we have the first order derivative term, which is the convection term. And then we have the second order derivative, which is the diffusion term, okay? So C over here is the convection coefficient. And then the nu over there is the diffusion coefficient. And those coefficients will determine how well, for example, a material, move from one location to the other location. So that's the, convection coefficient. And then nu is, certain physical can be, passed along from, one location to its neighborhood. So that's what's determined by nu. So in this setup, okay, this whole thing over here, so except for the time derivative, this whole thing over here is basically our nonlinear operator, okay? And that nonlinear operator is, parameterized by C and nu in our case, right? And that nonlinear operator does is to take a function u and then spit out the derivative, du dx minus d square u dx square. Okay. Generic nonlinear PD. So in this example, we have a linear PD, but you can see that any generic nonlinear cases can be covered by this representation. Oh, actually, one thing I forgot to mention is that there are some PDEs where we have the right-hand side comprised of some function, which is called the control input. So robotics, for example, the right-hand side typically, indicate the control input coming from the motors or some, other, actuators. So for pin, we do not consider those right-hand side, okay? Although there are a lot of papers in the literature that handles the control inputs, okay, inside of the pin. For the control input, in case you have a control input, it's a little bit more complicated because the control input is a separate thing and than the physical quantity u, right? The control input is the thing that is independent, and that independent input will, change the response of the system, right? So in that case, you're going to need to model the control input separately than the neural network representing u, right? And then you gotta hook them up together. But because of the complexity, we do not consider that in the scope of this class. But hopefully, after learning this, generic problem setup, you should be able to, read the relevant literature and then, see what's going on. All right, so Raisi et al., those are the people who first proposed the physics-informed neural network back in 2018. And in their paper, their actually pin paper is comprised of two parts. So there are two separate papers, part 1 and part 2. And in each of those parts, they propose a slightly different use cases of pin. So the first part, they talk about the data-driven solution of PDEs. So given a partial differential equation, how can we solve those partial differential equations using a neural network is the part 1 of this paper. Whereas the part 2 is what they call the data-driven discovery. So it's a slightly different nuance. In case of the data-driven discovery, you do not have the actual parameters. So last time we saw, the zeta and the omega 0, right? Those were the physical parameters in our harmonic oscillator system. And then we started from the assumption that, those parameters were given. We knew those parameters. But in many, real world scenarios, there may be situations where you do not know those parameters, but want to determine them from some sort of an experiment. So let's say instead of knowing the zeta and omega, let's say you only have some, video recording of a spring mass damper system, and then you track the position of the of the mass, and then from there you want to reconstruct the damping coefficient and the angular frequency, right? So in that case, we're talking about a data-driven discovery of PDs. So I'll walk you through, those different applications, maybe with a slightly more sophisticated physics problem. system, you still do not have anything. So you want to figure out the model of, describing the system, but in the meantime, find the optimal zeta and omega, as you go along with the optimization. Yes. Yeah. Um, yes and no. We're finding the operator in the sense that we're finding the parameter lambda. We're not actually finding the operator. So what I mean by that is, let's say you have some totally unknown physical phenomena. Um, in that case, you don't even know what the nonlinear operators look like, right? So in that case, the neural network will not be able to discover physics for you. So the term discovery is, again, in my opinion, it's a little bit of a misnomer, because we're not really discovering the PDE, out of blue. It's more like you already know that overall the physics will follow certain equation. You just want to figure out the coefficients of that PDE. Yeah, yeah, just finding lambda. Yeah. So in fact, we're gonna see some, other problems, not today, but tomorrow and then Wednesday, where we have absolutely no idea what's going on about the physics. You just have some, measurements from experiment, and then from there you want to, truly discover what's going on. So for those kind of problems, PIN is not the solution that, the method that you're looking for, but there are other methods that could be useful for those. So, okay. All right. So data-driven solutions. Um, I know there's a lot of math, so but bear with me. So for data-driven solutions, we led U theta, subscript theta, to be a neural network with the parameters theta. So theta is a collection of weights and biases in your neural network. And with that U theta, what we would like to do is to approximate the solution function ut of u of t and x using that U theta. Now, the assumption here is that we're given two things. One is data. So the data must be given at some time t and the physical location x, right? And for those, t and x, we expect that there's, the corresponding physical value u, right? So in terms of the notation, we use the superscript I with the parentheses to denote ith point in your data set. So, again, either from an experiment or some sort of a numerical simulation, we assume that we have this, tuple of t, x, and u. And then that is what for the data loss. And then, another thing that must be given to be able to driven solution, problem equation, including the, actually not some, but the entire set of parameters must given so that you can define the physics informed loss term, right? So those two are the most crucial things to define the loss term. for the training of PIN. And then from there, our objective is to train the neural network U theta, or figure out the optimal set of parameters theta that minimize the following objectives. One is the data loss, and then the other is the physics loss. So the data loss is the usual mean square error, and then the physics loss is, like we saw, the residual of the partial differential equation. Hmm? Yes, yes. So if you have both, physical experiment data and numerical data, then you probably want to treat them differently. For the numerical data, since the numerical data is deterministic, I think practically what people do is to add some noise to inject some uncertainties. Otherwise, the model training can be biased to the deterministic set of data, right? So yeah, they must be treated differently, like you said. Does that answer your question, or okay? Any other questions? Now, a little more on the physics informed loss, or the PD residual term. The collocation points are the points, like I said, defined as the pair of the location in time and the location in space. And like I said earlier, you do not need ground truth value with physical quantity. So note that there's no U involved in the definition of the physics informed loss. So somebody asked, what is the distribution of those collocation points? So usually we consider the uniform distribution in the space-time. So what that means is, whatever the range of, the time interval is, and whatever the, your physical domain look like, your best bet is to, just uniformly sample points in that space time and location points accordingly. There are some fancier, like I said earlier, methods to sample the collocation points. So instead of the uniform distribution U, you can sample points from some arbitrary probability distribution P. Okay? So similar to what you do in traditional numerical simulation, you can adaptively sample T and X. So the probability P can be a heuristic where you evaluate you increase the probability of sampling as you is, I don't know, violent. So determined by the magnitude of the gradient, for example. If the magnitude of the gradient is high, that means there's something, violent, something interesting is going on, some dynamic stuff is going on. So in that case, you can increase the probability of sampling. So there are a lot of different sampling methods, and we're going to see some of them in later slides. But essentially, the uniform distribution is kind of the default setting if you don't know where to begin with. So are you concerned about like moving boundary problems? So for the initial condition, I mean, you don't have to worry too much about it because um, the user pin. So for the initial value problems, initial condition is given already. So you can sample. Actually, initial conditions are usually fed in as data loss. So if you're given an initial condition, then you already have some ground truth, right, at time t equals to 0, and those ground truth data points can serve as the data loss. For the boundary, it's the same thing. It's a uniform distribution um, over the Cartesian product of the time interval and the boundary. So what that means is we're considering if you have some complex, geometry to define the boundary, we're considering that, during the uniform sampling. So again, if you have a CAD model, for example, then you want to sample points inside of that CAD model if you're talking about some solid mechanical problem, or if it is some fluid phenomena with certain boundary condition. Again, you got to consider the geometry when you do the sampling. So this very definition is generic enough to consider to include all kind of boundary conditions and additionally a little more sophisticated to implement, but theoretically speaking, there's nothing that prevents you from including those boundaries. Does that answer your question? Mm. Yeah, yeah. So here I brought you know, a slightly more sophisticated example, which is the heat equation, slightly more sophisticated compared to the harmonic oscillator. We're still in the very, simple case. Um, Heat equation is a, very simple PDE that describes the diffusion of heat through a given region. So the equation looks like this, where lambda is essentially the diffusion coefficient. And then what the heat equation says is that the rate of change in temperature is basically the same as the second order derivative or the curvature of the temperature distribution. So when there's a bump, for example, of the temperature distribution, that bump will produce some, large second derivative, right? And because of that bump, the heat will flow in the direction of, removing that bump. And then, after a certain period of time, the temperature will reach the equilibrium where, it is the same everywhere, right? So that's what this equation, stands for. And our goal is to find the solution function u given the diffusion coefficient lambda, as well as the initial condition. So initial distribution of temperature is already given. So it's an initial value problem. So this is something that we're going to see after the break with that, PyTorch session, within that PyTorch session. But here we consider that the initial condition is given as a sine function. So to make it simple, we have a rod, okay, of the length 1 meter. And then over that rod, we have the temperature distribution that looks like this. The temperature is normalized onto some scale ranging between 0 and 1, so that we don't get to handle like crazy large numbers. Now, the reason why I brought the heat equation as an example is because heat equation is one of the very few PDEs where the analytic solutions are known. For most of the PDEs, there are no known solutions, so there's no ground truth that we can compare against. But in case of the heat equation, the ground truth of the heat equation is analytically given. So in case of this initial condition, this is essentially the analytical solution for this initial value problem. As a matter of fact, this condition, you can describe the solution function u at arbitrary time t. Okay, so no matter how crazy your initial condition is, the solution is going to be this, the exponential part, times that crazy function describing your initial condition. So that's one of the really nice property of heat equation. And later on, so this is kind of a preview of tomorrow's lecture, actually. Somebody noticed that many of the initial value problems are in the form of some operator times the initial condition. Okay. So instead of learning the u directly, what about we learn self is another kind of way of thinking about physics learning problems, right? So you could learn the u directly, right? You could fit your neural network directly onto the solution function u, but you could also learn called the solution operator. So that is, by the way, what's called a neural operator approach, which is going to be the topic for tomorrow. And then, even more clever way is the solution PDEs will always look like and instead of learning this entire thing with exponential term included, what the term over here, right, inside of the exponential function is another idea that you could employ, which is called a physics-aware recurrent convolution, or PARC. Okay, but that's actually what my group has been working on. So, just as a preview in connection to the other problems, in today's lecture and then the last Friday, we've been talking about the way of approximating u directly using neural network. But then we'll see that that kind of methodology can create a lot of problem because the u itself can be highly nonlinear. You know what I mean? Like the harmonic oscillator, it's a linear ODE. But despite the fact that it's a linear ODE, the final trajectory, right? The curve itself is very nonlinear, right? So if you are to, if you consider a neural network as a curve fitting, right? You're fitting the curve on this crazy trajectory versus the operator itself. Again, in case of a harmonic oscillator, it's exponential of some matrix times t. Okay. So it's a linear matrix at the operator level. Okay. So if you train your model on the operator instead, I mean, instead of the solution function itself, you can simplify the learning problem from a very highly nonlinear curve fitting problem to, much more linear line fitting problem. And obviously, line fitting is much, simpler than curve fitting. So that's kind of, the evolution of thoughts that we're going to be seeing, throughout this week. So if that doesn't make sense, don't worry, we'll get there. But for now, we'll just move on. So in terms of how do we solve this heat equation using PIN? So in terms of the design of the neural network, what we're going to do is to have T and X, the input to the neural network, okay? Because we are talking about 1D heat diffusion, right? We have only one tangential rod. We only need one variable for the position vector and then one variable for time t, right? So those two are the inputs to the neural network. And then what happens is we have a bunch of fully connected layers, or the linear layers, right? And then at the end, we spit out, the temperature U, okay, as the output. So in terms of the neural network design, now we have, repeated the same thing multiple times. So at this point, you should be able to parse code over here. So we have a bunch of linear layers, and then the way it works is, you take the linear transform, and then followed by the exponential ReLU, and then we repeat that a few times, and finally spit out the final output. Now, in terms of the physics-informed laws, this is something that we learned last time, torch.autograd.grad, right? So in this way, you can take the derivative of any arbitrary, any sophisticated function, as long as you have a computational graph available. So what happens is we have two parts. The first part is where we define the data loss. The second part is where we define the physics-informed laws. The data loss, super simple. For given input, you infer the model, right? Make the model predict something. And those predicted temperature values are then compared directly against the ground truth outputs. And that's what defines the data loss. So data loss, super simple. The physics-informed laws might be a little more sophisticated, but as long as you understand how torch.autograd.grad works, then, again, this is not, terribly difficult. So for the physics-informed laws, first of all, we start with some collocation points. And given those collocation points, we have predictions here. So we have a slightly different, variable name to distinguish them, but, we have the, predictions basically. And then using the autograd gradient, we take the derivative of this prediction with respect to the collocation points, and then we have the derivative. Now notice that since we have n, we have two derivatives, okay? So the first part of the derivative is dt, the second part of the derivative is dx. And in our case, for the heat equation, we only need a dx part. And the dx part is derivative. There we go. So here's a setting. Here's more graphical, view of what I just walked you through. We're gonna actually see this in PyTorch after the break, but just to give you an idea, we have the initial condition, right, given already, and that is what defines the data loss. So the red dots over here is the data loss. And then we're going to assume that we do not have any other ground truth data loss, okay, to solve this heat equation. So we're using a neural network as kind of a numerical solver for this differential equation. Okay, we just start from the initial condition and that's it. Now for collocation points, we're going to set a mesh grid of 12 by 12 grid points. Again, here I just uniformly sampled, but I could, for example, have more collocation points earlier in time because I know that in the diffusion equation, the dynamics is more interesting at the beginning. And then once you converge, once the temperature diffuses, then the dynamics is not going to be as interesting as before. So I could, increase the density of the sampling with smaller time t, but here, for the simplicity's sake, we're just using a uniform sample. Well, actually, I should have explained how to read this plot. So for those of you who are not, in the mechanical, major, this plot may not be, as familiar. So we have the evolution of time, okay? And then here's the position x. So the rod is in this direction. And then the temperature distribution. So imagine a cross section of this surface, along, this direction, right? That cross section is what represents the temperature distribution at time t along the direction of the rod. Okay, so we have some, physical rod, and then initially the temperature distribution was like that, following the sine function, and then it diffuses and then kind of flats out, as you can see, as the time evolves. And here's the animation showing the training process of PIN for that particular setup. So see, initially, it's a flat plane. So the blue grid is the PIN. And initially PIN is like a flat surface. So that is the trivial solution. At the very beginning, without the data loss terms, the easiest way of, reducing the physics informed loss is by saying, oh, there's nothing happens in the temperature. It's constant everywhere. That's the easiest, trivial solution. So we start from there. And then because of the data loss, initially, the network fits the red dots predominantly. And then as we repeat more and more iteration, you can see that the blue surface gets kind of deformed to fit the actual physical process. Any questions so far? It's funny. It's funny to see that the CS side of the classroom, last week was like, very engaged and following very well, whereas the engineering side of the classroom was struggling last week. This week we have the opposite. The engineering side over there is doing great, and they're nodding their head. Yeah, that makes sense. And then the CS started to be like, "What the heck is that?" We assume that the initial condition is given. Yeah, yeah. Laws. That's what happens. And we do, sorry, I'll get to you. We do have collocation points at time t equals to 0. So that might answer your question as well. Yeah. So right. Um, you could, for example, run direct numerical simulation for a few time steps and then produce some data points and then use pin to fit the rest. But I don't know, that doesn't sound very realistic to me, right? I mean, if you're in a simulation lab, usually running the simulation takes a lot of time, and the whole point of doing pin is to avoid that time-consuming process of running simulations, right? So, yeah, so that's why, but it doesn't mean that you cannot have the data loss somewhere else than time t equals to 0. You can very well have whatever data points you want to have. Yes. Yeah. Yeah. That is a very big possibility of that happening. Yes, that's true. Yeah. And that you're right. So in fact, just among us, it took me a while to get this animation. It was very difficult to fine tune the parameters and things like that. So, um, and despite that, you can see that the pin is not perfectly accurate. And then I tried, more than 20,000, steps of iterations. I ran it all the way up to 100,000, 200,000, 300,000. It still looks like that, even for such a simple problem like the heat diffusion. So um, that's kind of an inherent, I guess, inherent downside of PIN, which is, the physics and form loss is the only thing that drives um, the training procedure. And then, you may end up in a erroneous solution like that. Um, is one thing I want to say. The other thing I want to say is, um, this is something that we're going to be talking about later in this class. But the data loss and the physics and form loss doesn't necessarily are aligned together. So reducing the data loss doesn't necessarily mean reducing the physics and form loss, and vice versa. Reducing the physics and form loss doesn't necessarily mean reducing the data loss. So during training, what happens is the data loss term and the physics and form loss term produce the gradients that are in the opposite direction. So the data loss term suggests that the model should be changed in this direction, whereas the physics informed loss suggests that the model should be updated in the other direction. And those directions can conflict. And as a result of that, sometimes actually, it kind of diverges where initially it sort of, start to converge that, to look like this, but then all of a sudden it pick up in some weird gradient and then, the solution kind of goes crazy. Or it stales like this and then never able to, be perfectly accurate. So those are kind of the limitations of PIN that are inherent to the design of the method. But if you have more data, then yes, I think the performance of the network is going to be much better. But you will still have that issue of conflicting physics informed loss and the data loss. So, yes. Mm. Yes, for sure. Yeah. So we're already, criticizing the limitations of PIN, and that was actually going to be the topic of the later slides. But you're absolutely right, because the dilemma here is, if you want to, make it more accurate, you probably want to add more collocation points, but then adding more collocation points means more computational time. So, that is kind of the trade-off that you have to fight. Yes, yes, yes. So if you have a boundary, um, some interesting geometric boundary, then oftentimes, I mean, the collocation points needs to be assigned near those boundaries, and then you're going to need a lot because, like in case of Navier-Stokes, for example, the fluid behavior will change dramatically near those boundaries. So when you have like a sharp, protrusion or anything like that, you're going to need to allocate a lot of collocation points over there. But then computationally it becomes super expensive, and it becomes like, oh, I would rather just solve a you know Navier-Stokes equation directly as opposed to training this thing, because it takes more time to train PIN and to solve the numerical solver. So, any other questions? All right. Speaking of Navier-Stokes, here's another example. Unfortunately for this one, we're not going to do it in the class because, like I just said, this takes forever. So I frankly don't see the reason why one would use PIN as opposed to direct numerical solvers, especially if you have high Reynolds numbers and things like that. I personally don't find the practical need of using PIN, but I mean, still, this is kind of an interesting idea. And then, pins obviously have evolved. So the original, formulation of Raisi et al. May not be useful for solving complex problems like Navier-Stokes, but there are other variants of pin that might actually be, practical in this case. But again, for the purpose of this class, we're going to stick to the original, formulation of Raisi et al. So Navier-Stokes, in case you don't know, is an equation that looks kind of like this. It's an equation that describes a flow of water or any fluid object. So if you're a mechanical engineer, this is probably something that will ruin your third year and fourth year in undergraduate. And then if you, are unfortunate enough to take the career in aerodynamics or fluid dynamics, this is something that you will struggle with for your entire life. But here we have a two-dimensional case, and it's incompressible, so it's a relatively simpler form of Navier-Stokes, which happens to look like this. Okay, it may look a little, intimidating at the beginning. It's really nothing more than the combination of the first derivatives and second derivatives of u and v. So u and v here are the velocity of the fluid in the x component and the y component velocity. And then the x velocity and y velocity follow this this relationship where the rate of change in the x velocity, that's the u sub t, right? The rate of change of the x velocity is somehow governed by the velocity gradient, right? So the x velocity, the gradient of the x velocity in the horizontal direction, the gradient of the x velocity in the vertical direction, and then the dot product between the gradient and the current velocity. So that's what's called the advection term. And then we have the pressure field. So x component of the pressure field obviously affect the change in the fluid velocity in the x direction. And then we have the diffusion term over here. So u xx is the second derivative of x velocity along the x direction 2 times, right? And then u yy is the derivative of the x velocity in the y direction 2 times. And that is what defines this whole thing. And then mu is what's called the viscosity. So yeah, so in case you are from engineering background, this might be a good opportunity to kind of brush up what you've already learned. If this is the first time seeing this equation, don't worry. Just get the feel that the time derivative is described in terms of the first order and the second order derivatives. Something complicated going on, but this is what governs the flow of water, flow of air, all kind of cool stuff. Oh, and then one thing I forgot to mention at the bottom is the conservation of mass. So here we have the x derivative of the x velocity plus y derivative of the y velocity, and that needs to be 0. And that is just a mathematical way of saying that, this amount of water flowing into a control volume and the amount of water flowing out must be the same. So that means that the divergence of the water flow needs to be 0, so that no water is created or disappeared. So again, training this takes a lot of time, so I didn't even bother to create a PyTorch example for that. But the original authors, they have published their code, which by the way is written in TensorFlow. But if since you already know PyTorch, TensorFlow syntax is not terribly different. So if you're curious, I encourage you to check out their implementation. But here we have vortex shedding. So somewhere over here is a cylindrical cross section, and then the water is flowing around that cylindrical cross section. So imagine you're driving a car, you stick your arm outside of the car, and your arm is roughly a cylinder, and then the air will flow around that cylinder and create all kind of weird kind of a demonstration of predicting the vortex shedding, behind the cylinder using pin. Obviously, for the Navier-Stokes equation, oh, sorry, one more thing. In this example, now we're talking about the discovery problem. Okay. So not only the velocity field, the pressure field are the unknowns. So the the coefficients, the fluid viscosity and the fluid density, those are the those are set at the level parameter. And this is nothing more than just like in terms of the PyTorch syntax, nothing more than just setting requires grad equals to true for rho and mu, and then you update rho and mu together as you train the neural network. We're going to see the the actual implementation, something equivalent to this in the Python. So they look pretty accurate, right? So this was kind of the demonstration that's in their paper. Now, one thing I want to mention though here, since some of you mentioned, asked questions about the boundary condition and things like that, they actually did a sneaky, thing of not presenting the cylinder, So they actually set a control volume behind the cylinder and did not really, present the result around the cylinder. And later on, people discovered that pins are not very good at respecting the boundary conditions. So actual predicted pressure, you can see that, the water sort of, penetrate into the cylinder, and the cylinder is now, filled with some flow of air or flow of water. And then they kind of, only presented this, this section of the vortex shedding phenomena. And then because of that, it kind of, sort of promoted other, directions of research, which is to, enforce the strict boundary conditions inside of pins. But that work is still kind of ongoing. So that is actually one of the sneaky things that we also discovered, among my students and I. We were kind of messing around with pin, and then we've been, facing with issues where, water keep, just into the, no matter how location points we set, near the boundary, it eventually goes in. And that kind of continuity, if it is something that the neural network will, struggle of modeling, because it's a curve fitting, it's a surface fitting in this case. And then if you have continuous boundary, you have a curve shape that is, kind of discontinuous, right? So fitting, yeah. So, pin being a regression model, have a discontinuities that, it'll struggle. Um, so that's something that I wanted to mention here. Um, well, I do think they have the bias in the model already, but despite that, somehow the actual pressure values are a little off. And then the authors did not, particularly give any answers to, why the color bar is different. So I don't know. All right. So the summary so far is, PIN at the end of the day is a regression model with some soft penalty defined by the PDE residuals. And then, we could essentially do two things, either, solve the, PDE where the solution is unknown, or on top of solving the PDE, you could also discover the physics parameters. So those are the two use cases of PIN. Pros, obviously, implementation of PIN is super simple. It doesn't involve any, complicated implementation. It's basically a regression model. The only thing that's added is the, PyTorch autograd.grad. And then as long as you can compute the derivatives and, implement your own differential equation, that's all you need to do, right? And the implementation is super simple. So it gained a lot of popularities. And then, from the perspective of the applied physics community, you have two things, right? Fancy, deep learning. That's the big buzzword in the academic community. And then it sounds like the deep neural network is respecting some physics, or based on some physics principle because of the namesake, right? Physics informed neural network. So it gained a lot of popularities in the CFD community, in the mechanical engineering community, civil engineering, like wherever the discipline is, wherever you need the physical equation and want to somehow model that using data driven method, it gained a lot of popularity. And then um, you know like many other technologies, when you have a shiny hammer, everything started to look like a nail, and then you want to hit the nail with that shiny hammer. So and I think until now, like even until now, is considered to be a shiny hammer for to a lot of people. And then you get to see a lot of publications that involve PIN, and then people solve some kind of an equation using PIN. But like I mentioned, there are a lot of challenges and also research opportunities. So the original formulation of Raisi et al. Especially is not particularly useful in many reasons. And then there are a lot of research going on to improve PIN, make things better. So here is one particular paper by Krishna Ryan et al. In 2021, where they kind of investigated PIN more that, and then they kind of came up with a set of benchmark test problems to reveal pros and cons of PIN. So one of the benchmark problems that they came up with is the 1D advection equation. So 1D advection equation, the partial derivative of u is described as a linear function of the spatial derivative, first order derivative. And 1D advection equation describe a phenomena where the matter a matter moves in one direction. There's no diffusion, there's no creation of the matter, anything like that. It's just a pure transportation. So you have the initial condition described as sine x, and then according to this equation, what happens is the sine wave just moves. Okay. And then in their setup, we assume the periodic boundary condition so that, at x equals to 0 and x equals to 2 pi, the values are the same. So if you were to train Pin on this problem, you would need the PD residual, the physics informed loss, right? The initial conditions serve as the data loss terms. So for a given xi, we know that at t equals to 0, it has to satisfy sine x. And then we also have the boundary condition, and the boundary condition is another kind of data loss term. So we have data loss term coming from the initial condition and the boundary condition. And then we have the physics informed loss term. And guess what? So let's look at the exact solution first. So this is the exact solution. This is the x direction. And then this is the y direction. This is the temperature direction. Time direction. What am I talking? So we have the x direction, the time direction. What happens is the sine wave, okay, initially on this x direction is evolving over time, okay? And then, like I said, the 1D advection equation describes the translation of the sine wave. So if you, in your mind, if you, take the cross section of this chart, right, in the vertical direction, you will you will kind of see that the sine function is moving, from here to here. So, this is the peak of the sine function at the beginning, right? And that peak, as you can see, is moving in this way as the time goes. So that's what is, is governed by that equation over here. So if the neural network was perfectly accurate, then it should be able to produce this result, okay? Notice that the beta, the advection coefficient, or simply speaking, the speed of translation is relatively high. So beta equals to 30 is the situation we have. So, when beta is large, obviously the stripe pattern is gonna, be steeper, right? When beta is small, then, the translation will happen more gradually like this. Now, with that in mind, look at the Pin solution for beta equals to 30. Okay, you will see that the initial, sine wave segment gets advected properly, but then in terms of the boundary, the periodic boundary condition, it's not really respecting the boundary condition. And in fact, it fails to predict anything, after time t equals to, I guess, 0.2. 0.2 is roughly when the initial sine wave kind of, makes its, full translation, right? And then after that, it doesn't really, predict anything. So, from this, we kind of see that pins are actually not very good at preserving the boundary condition. And I just mentioned a few slides ago that the Navier-Stokes example, they somehow sneakily did not report the cylindrical cross section in the paper. If you look at the error rate as a function of beta, you can see that with the growth of beta, the error kind of sort of jump up quite dramatically. And again, We have the low velocity regime on the left. We have the relatively higher velocity regime on the right. And then the error kind of goes up quite dramatically. And notice that this is a log scale. So the jump of error is actually more dramatic than what you see from this chart. Are we doing on time? Okay, perfect. Here's some more examples. So when beta equals to 10, like I said earlier, it's a relatively slow speed. And in that case, it, preserved the periodic boundary condition. And then it was able to, make the prediction accurately. Here's the error plotted over that, xt space. And then we're in the order of 0.02. So relatively small error, about 2%, roughly speaking. So everything looks good. But then the moment beta goes up, you can see that as the beta goes up, the stripe pattern becomes, much more frequent and then, steeper. And then you can see that the model just gives up, preserving the periodic boundary condition, and then we get to see a lot of errors. Any questions so far? Now, the fact that PIN struggles with boundary conditions and advection in general doesn't mean that there's no hope, right? So if you still want to use PIN for whatever problem that you're working on, there's one well-known strategy called the curriculum training. So to be fair, if the speed is too high, if beta is too large, to be fair, that's already pretty difficult problem to predict. And if you let the neural network to predict that from the get-go, it won't be able to make a good prediction. Since we're using the brain analogy, neural networks are kind of like an intellectual creature, like a little child. Initially, it doesn't know anything about physics, and all of a sudden, you present Einstein's general relativity to this little kid. I mean, there's a good chance that this kid will be lost, right? Understand nothing. You got to start from a simple physics equation. Maybe F equals to ma is a good starting point always, right? And then from there you develop intuitions, and then you have to kind of train students step by step. You don't want to intimidate them with some really difficult example from the get-go, and then everybody will feel lost. So same thing, if we consider a neural network as kind of a student trying to learn something, you probably want to start with a simpler physics problem and let it learn to predict those simpler problems. And then gradually you increase the complexity of the problem. So that is the idea of curriculum training. So in practice, what this really means is, as we saw in the previous slide, when beta equals to 10, it does a fairly good job, right? So what you can do is to start with beta equals to 10 and pre-train the neural network with beta equals to 10. And then you increase beta by a little bit. So let's say instead of 10, now beta equals to 15. Generate the data, right? And then present beta equals to 15 to PIN, and then start from the previous training session. You update the model, and in that way you make PIN predict beta equals to 15. And then after that, you increase beta a little bit, make it 20, let's say, and then you fine tune the weights of the neural network with beta equals to 20. And then you basically repeat that process all the way up to beta equals to 30. And as a matter of fact, with that training strategy, the authors were able to train the same pin model on beta equals to 30. Now we have, pretty good prediction result. And, quantitatively speaking, here's a table comparing the error, okay, the regular training of pin on the left column, and then the curriculum training of pin on the right column. And you can see that the error rate, there's a multiple orders of magnitude difference in terms of the error rate. So, almost all cases for the training of pin, curriculum training is the must. So what that means is, you start from some simple, relatively simpler situation where, the fluid speed is, much slower. There's not a lot of action going on. You train the model and then, let the model converge first. And then from that, converged model configuration, now you increase the complexity of the physics problem, and then keep repeating the process is what you can do to improve the model. Does that make sense? All right, so here's another canonical benchmark, again from the same review paper. So now we consider 1D reaction diffusion equation. So reaction diffusion equation is an equation where, again, we have the physical quantity that evolves over time, and we have still 1D. So we have one-dimensional distribution of some physical quantity, and then that's evolving over time. And it's, it is some sort of like a, equilibrium process, in the sense that, you start from some distribution, but then afterwards, it just set to, constant everywhere. Now, the diffusion term obviously, describes the diffusion phenomena. So the quantity kind of spread to the nearby region. But then the reaction term over here describes the creation of, of the material, and so on and so forth. Again, this one is slightly more complicated, equation compared to the previous one. And, for the exact solution over here, this is kind of the expected physical behavior of the system. But if you look at the pin solution, we're kind of far from exact. And the reason why we're talking about this particular equation is because we have some sharp boundaries. So we have this, sharp, red color there. And then, this is kind of the, where the value U sort of drops dramatically, right? And then now we become to have a really low values in this region. So the ability to model that kind of sharp features is what we're testing over here. And unfortunately, PIN solutions, for none of those cases, PIN was able to predict it properly. So for that, a very, typical, resolution of that problem is either of these two. One is what's called a sequence to sequence training. So instead of, having the ambitious goal of predicting everything over the entire time, space time, all at once, you can, divide the problem into smaller sequence of time. So you set some small delta t, and then, using that, small interval of time, you basically train PIN, and then, make prediction over there, and then, slide the time window to the next, delta t, and then solve the problem on that, next segment of delta t, and so on and so forth is one possibility that you can take. The other thing is the adaptive sampling, like what we've been talking. So, those sharp features, obviously, if you have a uniform sampling of collocation points, you're going to lose those sharp features quite a bit versus, when you do the sampling of the collocation point, you can have more collocation points near, those sharp regimes, right? And in that way, you can improve the prediction accuracy of PIN. And oftentimes the adaptive sampling and the sequence to sequence training happens together. So you make a prediction of the first small delta t, and from that prediction you can have an idea of where the sharp features exist. So then when you do the next prediction for the next delta t, then you add more collocation points those near those sharp features, and then you basically repeat that process, and in that way you can have an adaptive samples of collocation point. And with those, obviously, you can have a better modeling accuracy. So this is kind of a very common, very well-known solution to some of the problems of PIN. One final thing I want to mention. I mean, you guys did a great job today, because you already mentioned, a lot of potential issues of PIN, and you asked a lot of questions already. So I sort of explained that as I answer your questions. It's a good job. But just to kind of reiterate, optimization is a big challenge in PIN. So this is kind of a graphical visualization of the loss function, the mountain that we're climbing, or the reverse image of the mountain that we're climbing down. The moment we add physics laws, we start to have lots of wrinkles. Okay. And in terms of the gradient descent solver, if you have lots of wrinkles, it is inherently more difficult to optimize. So initially we had this nice sort of a plateau, and then in the middle there was a hole, right? So from the perspective of getting to the bottom of this hole, you start from somewhere, right, on this plateau, wander around following the gradient direction, and then the moment you get nearby the hole, you just converge to the the global optima. Versus now we have the physics laws, and then the physics laws terms add a lot of complexity to the terrain. So it's no longer the problem of just wandering around this surface and then fall into this hole, but you have to kind of overcome all this noisy local minima, right? And then if you're lucky, you will discover this point over here, but most of the time, you're not going to be able to discover that very well. So sort of going back to the earlier question, what you want to do is to start the small, way applied to physics laws, so that virtually we have a situation where we can ignore the physics laws, and you get to the hole as close as possible. And once you get close enough to the hole, you increase the importance of the physics laws, and then make it more rigorous, so that you can converge to a better solution. Is the possibility of what you can do. This, by the way, this beautiful visualization is done through a really nice mathematical method. And here, let me show you. A website called lostlandscape.com. So this is not particularly restricted to physics informed loss terms, but this is a website where you can see lots of visually stunning, you know, illustrations of how the loss functions of neural networks look like. Look at this. It's beautiful, you know, visualization of the, you know, loss function. And then you can see that there are lots of, you know, spiky, you know, local mins, right? So that's why, you know, it's hard to train a neural network. So here, this is my favorite figure. Um, you know, what it does is to compare different hyperparameters and how the loss function landscape change as a function of hyperparameters. So under certain setting, you have a nice smooth, you know, surface near the minima. But then for the settings that are not, you know, so great, you get to see this noisy spikes, which is inherently harder to optimize. And there's a really nice paper associated with um, this website called Visualizing the Loss Landscape of Neural Networks. Yeah. So if you're curious, I encourage you to take a look at you know, the website, thelostlandscape.com, and then the paper associated with it. Seems like the internet today is a little slow, so maybe instead of waiting, I'm going to move on. So this visualization is created based off of that you know, loss landscape paper. So if you want to have a better understanding of, you know, what kind of problem they're solving, it like this is a one very good way of, you know, enhancing your understanding of the problem. Yeah. So here's another kind of, you know, perspective over here. Um, you know, we have the loss landscape for the same problem. And, you know, as one of you already asked, we have the coefficient over here. So when that coefficient is small enough, then we have relatively smoother surface. Versus when you have a larger coefficient, then you start to see lots of wrinkles, which makes it much harder to optimize. Yeah. So here's some comparison in terms of um, you know, how we could. Sorry. Here's the comparison of the error of training of the prediction for a 1D convection problem. And here, the lambda is the physical parameter. So obviously, the physical parameter also determines the landscape of the loss function. And in a nutshell, as you can imagine, if the physical parameter um, goes into some, you know, violent nonlinear regime, right? So in case of fluid dynamics, if you have a Reynolds number that goes beyond, you know, maybe 1,000, 5,000, right? High Reynolds number regime. Obviously, the loss function landscape is going to go crazy, and it becomes much harder to train. Or in case of you know, structural mechanics, if you have a stiffness, you know, coefficients grow, then you have a really stiff system. And in those cases, again, you get to have an inherently difficult problem to solve. So again, the solution to that is the better choice of collocation points. So here we have another kind of sharp problem where, again, we have a 1D problem, and then it's evolving over time. And then this, you know, evolving field kind of creates the huge contrast over here. So you could have the collocation point, you know, redistributed like this so that we have more collocation points in the middle. And in that way, you could improve the prediction accuracy. But still, it's not terribly helping. So this is actually what I encourage you to do, with that PyTorch example. So in the example that we used, we had a relatively small angular frequency and then, a moderate amount of damping. And we were able to, make a pretty good prediction. But now we have, smaller damping and then a higher angular frequency. And as you can see, it struggles. And the number of iterations keep going. So it's not that, it has prematurely converged, but it is still kind of converging, but it doesn't seem to be able to find the global min. And the prediction result is way off, right? After a certain time t. Again, if you compare this with the landscape over here, it'll start to make sense. So if you have a more dynamic problem, the loss function landscape is going to be much more complicated, like on the right, and obviously training the model is going to be really complicated. So with that, I'm going to wrap up the physics informed neural network lecture. After the break, we're going to come back to the PyTorch example. One thing that we haven't discussed yet is the data-driven discovery of the equation. So we're going to see that example using the harmonic oscillator. And then I'll show you the heat equation example, just so that you have some more sophisticated example to connect with your problem. So thank you all, and I'll see you in roughly 30 minutes.
I think we still have one more minute, but your faces tell me that you're very eager to start. So why don't we start 1 minute early, and then let's see if I can end a minute early. So last time in the PyTorch session, we talked about the implementation of PIN on the harmonic oscillator problem. So we went over the code and we sort of look into the implementation details. So just as a recap, this was essentially what it looked like. The data loss term was only just 2 lines, right? You make a prediction, and then you compare that prediction with the ground truth label. So in this code, the variable named output is the ground truth, and that gets compared against the prediction in the mean square error sense, and that's what defined the data loss. And then the physics informed loss was essentially, you take the automatic differentiation of the model prediction. For the physics informed loss, we saw that the collocation points are the points where the model is evaluated. So for a set of collocation points, we make prediction and then take derivatives. And then those derivatives are used to calculate the residual of the governing differential equation. And that's essentially how you define the loss function. The total loss is defined as the data loss plus the physics informed loss. And that's pretty much it. And then, we saw that, from that formulation, we could train a model like this. And then even with a small number of training data, with the help of collocation points and the physics informed loss term, we were able to construct a pretty, reasonably, accurate model. Now, before we move on to the next example, which is the 1D heat diffusion, let me first, show you the data-driven discovery, because that's the part that might be a little hard to understand without seeing the code. Although if you look at the code, it's actually pretty straightforward. So for data-driven discovery, we consider a scenario where we only have the observation, but we do not have the knowledge of the physical parameters. So unlike the previous scenario where we knew already the physical parameters, now we consider a situation where we do not have an idea of the physical parameters, and therefore we want to approximate them using physics-informed neural net. So here, what we're going to do is to pretend that we do not know the omega 0 and zeta, okay? Even though we, sort of do know, because we created the ground truth out of, the values that we know. So as a matter of fact, we used omega 0 equals to, we use omega 0 equals to 2 pi, and then zeta equals to 0.15 as the combination of the physical parameter to generate our data. So that's the answer that we're going to figure out. But again, like I said, we're going to pretend that we don't know those values. So in this problem setting, what we do is to make observations for the first 3 seconds in time. We're going to take some number of samples. And then, so this is a ground truth sample that we generate. And then on that sample, we're going to add some noise to emulate the real world scenario. So consider, again, a where you have some experiment device to track the position of the spring, right?
and then you measure the position of the spring, over a certain time period. And then from that measurement, you want to, calculate the, angular frequency and the damping ratio, right? But then, no measurement devices are perfect. So we're going to assume that there's a little bit of noise added, right? Which is a reasonable assumption. Now, graphically speaking, this is going to be the training data. So now the situation is a little different, right? In the previous example, we had only, few samples at the beginning, and then our goal is to predict what's going to happen in the future. Now we have, the entire time covered in the training data, but now we have, some noisy examples. And then from there, we would like to reconstruct the omega 0 and zeta. Does the problem setup make sense? Okay. Now, this is the implementation of the data-driven discovery problem. The only difference, okay? The only difference now here is that the value of omega and the value of zeta is now defined as a PyTorch tensor that requires the gradient. So notice that omega underscore prediction, so that's the predicted omega, not the ground truth omega. And then zeta underscore prediction. So those two variables are initialized with some random number, and it's a PyTorch tensor that requires the gradient. Because our goal, our plan here is to optimize the predicted omega and the predicted zeta, okay, as we optimize the neural network. So not only the neural network parameters, but also the omega and zeta will be the parameters for the training, for the search. So that's why we're going to require the gradients. Now here, if you look at the optimizer setup, so I have the same atom optimizer, but now the list of parameters that are being optimized, you can see that we have the list of model parameters, and then we have zeta pred and omega pred concatenated on top of that list. So in the previous setup, the only thing that were being optimized were the model.parameters. Now we have, on top of model.parameters, we have zeta pred and omega pred. So that's the only difference. Note that for those of you who are new to Python, when you have lists, the addition operator simply means concatenation. So you have a list of ABC and a list of DE, and then you add them together. What happens is it's going to create a new list whose elements are A, B, C, D, E. Okay, so that's what's going on. So no matter like how many thousands or how many millions of parameters you have, at the end you're adding zeta pred and omega pred as a variable that is being optimized. Why are we using? Oh, we're just randomly initializing omega prediction and the zeta. You could do that. Yeah, you could do that. But without a knowledge of what omega and zeta might actually look like, a reasonable thing to do is to just initialize with some random value. But if you want to start with, I don't know, some specific value, feel free to do so. Yeah, that's not a problem. Other questions? Ask questions, because that's really what I have. Sorry, what? Repeat the question again. Yeah,
Well, like I said, pin itself is a curve fitting problem. So it is a curve fitting problem with the physics informed loss term serving as a smoothness. So you fit the curve, but you want the curve to be smooth. And then, mathematically speaking, the physics informed loss, you know, constrains the tangent vector of the fitted curve, right? Because governing differential equations are usually the ones that defines the relationship between first derivatives, second derivatives, and things like that. So those terms are regularizing the shape of the fitted curve so that you're not only fitting to the target data point, but also in between points you want to make them smooth according to some smoothness criteria. So yes, it's a curve fitting problem. So the search of omega and zeta happens over the entire real number line. So there is nothing that actually, bounds or restricts the range of zeta and omega in this setting. So if something goes wrong, in principle, this algorithm may return zeta and omega values that are way off the range. But then the risk of finding those weird values is very low because right physically they will not make sense, right? So but there's nothing explicitly constrains the range of search over here. Other questions? Yeah, if not, that's really it. So over here, the usual data loss term, nothing has changed. We have the usual physics loss term, nothing has changed. And then we're just doing the loss dot backward, optimizer dot step to fit the model. But internally, the optimizer has omega and zeta as one of the parameters that are being optimized. So that this one over here. So we have a very small number multiplied to, yeah, very small contribution because of the, well, if you have a larger physics, larger contribution of physics laws, it's not going to converge well. And this is multiplied because of that. Remember before the break we talked about the loss landscape and things like that. So because of that, it's really hard to optimize. So again, that's kind of one of the inherent limitations of PIN. So you got to have some small contribution like that. Otherwise, it's not going to converge at all. Yeah. So initially the data loss is going to be predominant because we're multiplying some really small number. So at the beginning of the training, the data loss term is going to be the predominant term. But then after the curve fitting is done, the data loss term is going to be relatively smaller. And relatively speaking, the physics loss term start to be, bigger than the data loss term, relatively speaking. And that's when the physics loss terms start to kick in. And then the curve shape is further optimized according to the governing differential equation. So that's usually the training process. You first minimize the data loss, and then let the physics loss kick in afterwards. So how do you determine that number? There's no golden rule. Like it has to be empirically determined. Hmm. Yeah. So the hope here is obviously that the noise can be compensated by introducing the physics loss term. But then again, at the beginning of the training, we're not even going to worry about that. But then once the curve fits, then the physics loss terms start to play the role and then smooth out a little bit. So here's the result of fitting that pin model on this data. So despite the existence of the noise, seems like the curve shape is pretty good, right? And then here's an animation showing the progress. And for this one, it converges slightly faster than the usual pin. So almost from the get-go, you can see that the predicted curve is pretty well aligned with the ground truth. And that's because we have lots of training data, right, all across time. Now, let's compare if the predicted zeta and the predicted omega is accurate. So here I printed the actual zeta and actual omega that I used to produce the ground truth data. And then at the bottom, I printed the zeta pred, the ones that we learned. So remember, we started from some random number, and then we let the 8th atom optimizer to figure out the zeta and omega value. And as a result, I got zeta equals to 0.14755, which is pretty close to 0.15. And then for omega 0, the ground truth is 2 pi, so 6.28. And then omega 0 predicted by the model is slightly higher than the ground truth, but reasonably good, right? If you consider the fact that it had noises and things like that. So this is really the discovery part of PIN. So it's nothing more than those physical parameters added as an additional variable to optimize. And then you just train that, optimize that all together with the model parameters. And then at the end, it'll converge to, something, a reasonable approximation of the ground truth values. So if you have some, experimental, measurements, like from, I don't know, whatever experiment that, you're doing, if you have a set of data like that, and then from there you want to identify what the physical parameter was, and this is one of the things that you can do to identify that physical parameter. One last thing I want to mention is that again, the term data-driven discovery doesn't necessarily mean discovering the entire PDE. Here we assume that already there's a known PDE form that was available, right? So if we didn't know, for example, the actual governing equation, the form of the governing equation, then there's no discovery. And there's no PIN, as a matter of fact, because PIN, the whole idea is, to minimize the residual of the, differential equation. But if you don't know the differential equation, there's no PIN. It's just a simple regression problem, right? Any questions? Yeah. It's available in the code, but I believe we're using the exponential ReLU. Yeah. SILU, or swish is the name of this function, and this is basically exponential ReLU. What do you think is the problem with ReLU? We already covered this. Yeah. So what do you? Well, let's see if you guys remember what we discussed already. What do you think is the problem? Yeah. If you take the derivative, you'll have a constant.
for ReLU, and then you take the second derivative, it'll return 0. So there is nothing to optimize, right? Look at the governing equation. We need the second derivative. Yeah, we need that. We need to evaluate the mx double dot. So double dot is the second derivative. Yeah. I don't think so. Because ReLU has a constant derivative. Sorry, I couldn't understand your question. Well, the first derivative of ReLU is a constant. With that constant, what are you optimizing? Nothing. You cannot optimize anything if it is constant, right? Second derivative is also constant, which is 0. So again, if it is constant, you cannot optimize anything. Because the whole idea of physics and form laws is to change the neural network parameters to minimize the residual. So second derivative, first derivative, the summation of them needs to be somehow, optimized. But if your ddx and dx are constants, then there's no optimization that you can perform. So the physics and form loss is not going to reduce. And as a result, you will probably, be just finding a regression model. Yeah, yeah. So always a good idea is to use an activation function that is infinitely differentiable, infinitely many times. In that way, you don't have to worry about anything, right? But if it is something else, then you may encounter a problem. And as a matter of fact, I encourage you to play with those kind of things. Again, the best way to learn this is by, just experimenting it, with the code. So even if you change it to, ReLU, it's not going to explode your computer. So feel free to do so and try to observe what happens. It's as simple as just replacing SILU to ReLU. And then let me actually show you a first few steps. Well, the last layer's output depends on the earlier layers, right? So no. So while this thing is training, well, I'm glad that you actually asked that question because so a linear layer or perceptron layer is essentially Wx plus b. And, W is a slope, B is a y-intercept. So what you get for a neuron is some line like this. And then by applying ReLU, what happens is you get something like this, right? Because ReLU, anything negative will be set to 0, and then the positive values will be just the same value. So this is the graph shape after ReLU. Depending on the slope and the y-intercept, you may have a collection of this or this
or, smaller slope, bigger slope, right? You will have a collection of all kind of different lines. So that's what the first layer does. And then the second layer, which is the weighted sum of the previous outputs, the second layer output is going to be essentially, some weight times this curve plus some weight times this curve plus some weight times this curve, and so on and so forth. So for the simplicity, let's ignore the other guys, but consider these two. So some weight times this plus some weight times that, you will likely get something like this, right? So, after the first layer, we had pretty simple shapes. But then after the second layer, by combining those simple shapes, now we have slightly more, sophisticated shape. And then, similarly, by combining the others, you should be able to have, more sophisticated graph shape like this. And then, in the second layer, you basically have a collection of this and this, maybe that, or something like this, and so on and so forth. Now, after another layer, we basically combine a little bit of this plus a little bit of that plus a little bit of this plus a little bit of that, and so on and so forth. And then as a result, we're going to have even more sophisticated, result like that. So by stacking up the, perceptron layers, you're adding more kind of curves, right? But then if you use the ReLU activation, okay, you're basically combining line segments, straight lines. And then as a result of, those combination, the best you can get is a polyline, right? Which is comprised of smaller line segments. Now, by using this kind of assembly, this is almost like an origami, right? You fold the line and then fold them, again. And as a result of that, what you would like to do is to do the curve fitting. So you have, for example, harmonic oscillation, and then you want to fit this curve by doing this. But if you use ReLU, then what you're going to get is some polyline approximating this thing. There's no smoothness, there's no, right? It's all kind of piecewise linear approximation of, of that thing. Now, if you take the first order derivative, the first order derivative is going to look like some weird step function, stair step function. Where if you take the derivative of that guy, you're going to get a little bit of constant over here, and then a constant over here, and then constant. See? And then if you take another derivative, so this is x, this is dx, and then if you take d dx, it's going to be 0 everywhere, right? So if you use the ReLU activation, you cannot really evaluate the physics-informed loss term, and you cannot really control the dx value and the ddx value, which is why it's important to have some, continuous activation. Okay, so the swish function kind of look like this, and then now we have a continuous folding of the line, so that after the assembly, you have some smooth curve. Okay. So let's go back to the training over here. So I just changed the activation to ReLU. And like I mentioned, you see this kind of line breaking. Yeah, it becomes a polyline. Yeah, and then, yeah, still okay, right? Not terribly bad, but you can see this like discontinuities and spiky shapes, and then yeah, so that's what happens essentially. So feel free to experiment with ReLU and other linear not linear activation, but other simpler activation functions, um, and then see what happens. Okay. So that was the harmonic oscillator, both the data-driven solution and data-driven discovery of harmonic oscillator. Now we're applying the same thing onto the heat equation. So the theory of heat equation, we already talked about it, so I'm not gonna go over that again. And the implementation of heat equation is pretty much the same as the harmonic oscillator. Except that the Colab version has a bug, I just figured. So for now, let me just use my local version. Oops. Version. I'll fix it later, but you can some apologies for that. Oh no, this is harmonic oscillator. Sorry. Heat diffusion. That's for the visualization purpose. So if you're new to Python, don't worry about that part. Interface may look slightly different from the Colab interface, but it's essentially the same thing. I'm just running it on my local machine as opposed to the Google computer. That's not the important part. The important part is so this example we saw already, during the lecture, but here's a closer look into the actual result. So here it is. So the first part of the code is really just for generating training data set. So here's an analytic solution of the 1D heat equation. And then over here is where we generate the training data. For the training, we're going to sample 15 data points along the x-axis at time t equals to 0. And then that's pretty much the training data that we're going to be utilizing. For the co-location point, we're going to sample 12 by 12 grid.
So 12 in the direction of time, and 12 in the direction of x is what we're sampling. And then as a result, this is kind of what we're getting. So up to this point, nothing terribly, difficult to understand. It's really just, Python code to sample the data and, whatnot. The most important part here is the model design and then the training procedure. So for the model design, we're pretty much using the same model as the harmonic oscillator case, except that now for the input, we have 2 dimension coming in because we have not only time, but also the position x as our input variable. But then other than that, it's pretty much the same. We have 32 dimensional. So a hidden layer with a 32 dimension. We have 3 hidden layers with the same number of hidden neurons. Feel free to play with the number of neurons, obviously. If you have more neurons, then you should be able to, generate more sophisticated curve. Also with the activation, I'm using CLU, but any continuous function that are differentiable many times could be an option for this. So 10H could be another option, right, for this one. So that's the model definition. Now for the training, we're using the same procedure. So we have the atom optimizer, and then we're optimizing the model parameters. So we're not solving the data-driven discovery problem. So this time we're optimizing the model parameters only. And then here in the for loop, inside of the training loop, we have the input tensor, input and output that are given by the data. So that's the training data. And then, we're making the inference of the model on the training data set. And then that prediction is compared with the ground truth label. So that, the good old data-driven loss, definition over there. Now, the slightly confusing part is the definition of the physics loss, because now we're dealing with 2 variables, t and x, as well as second derivative, right? So, but once you understand the principle here, and we since already saw the syntax for the PyTorch autogradient, for the first order derivative, we have the prediction on the collocation points. We take the derivative of that with respect to the collocation points themselves. And then we have the ones like. So we saw this last time when we first introduced the PyTorch gradient as a way of extracting the diagonal terms of the Jacobian, right? So PyTorch autograd, we basically calculate the vector Jacobian product as opposed to the original Jacobian itself. And I showed you this as a trick to extract the diagonal components of the Jacobian term. What those diagonal terms indicate is essentially the the derivative of the collocation point with respect to t, and then the derivative of the collocation, the prediction with respect to x. So we have ddt and ddx, they'll be obtained as a result of of that first line. Okay. The ordering follows my convention. So in my convention, I decided to use t as the first input and x as the second input. If you decide to implement in a different manner, so x as the first input and the t as the second input, then the order will change so that dx is going to be the 0th column, and then the dt is going to be the first column. But in my convention, t is first, followed by x. So if this line makes sense, then the second derivative should also make sense. Where for the second derivative, we're done with the, with this guy over here. So we completed our visits with the time derivative. The only time derivative heat equation is the dt term. So that part is complete, but the second derivative, we need ddx, right? So dx gets, into this I torch autograd, and then we're taking the derivative of dx with respect to the collocation point. And then again, same thing, we're doing the torch dot ones like, so that we can extract the diagonal terms of the Jacobian. The first term of the Jacobian is going to be dx dt, right? So second derivative of, of u, one's with respect to dx, and then, with respect to t, is going to be the first output of, derivative 2. The second output is going to be the derivative of this guy with respect to x again, right? Which is ddx. So in our case, we only need ddx. We don't need a dt dx, right? So that's why we're extracting the second derivative, the second element of the second derivative. So, this is the part that might be a little confusing because we have, more than one variable now, and then you're taking derivatives. And then, if the notion of Jacobian is not solid, right, in your mind, then this might be a little confusing. But when that happens, probably the best thing to do is to just write down on a piece of paper, and then see what happens, term by term, because things like Navier-Stokes, for example, it's going to be even more confusing because now you have the velocity field. You have to take the derivative of the velocity field. You have to take the derivative of the pressure field. So a lot more variables to take the derivative of, and then it can be a little more confusing. But just write it down on a piece of paper, especially in terms of the Jacobian vector product, and then things will start to be much clearer once you do that. So if that makes sense, the rest of the process is essentially the same. We have the physics loss term, as usual, defined as the residual of the heat equation. So we have dt minus diffusion coefficient times the second derivative. And then that's basically what defines the physics loss. And seems like some people in the audience are already bothered by the fact that the contribution of the physics loss this time is much larger because the residual happens to be smaller in this case. Again, how do I know? I tried it a lot with different combinations of the weight values, and then for this particular problem, because of the way we sample the data loss term, the way that we sample the collocation point, physics loss happen to be much smaller than the previous. Empirically, I decided to just go with 101. But again, there's no science behind it. You just have to figure out by failing multiple. So now running this is going to take quite a time. Actually, I should have ran this while I was explaining the code, but it's going to take a while. 30,000 iterations is roughly where you can find a pretty good fitting result. But yeah, it's going to take a while. So I guess I'm not going to wait until this cell finished to execute. But after the training is complete, After the training is complete, this is what you're going to see as an output. That is scary. Yes. Um, that's a great question. In theory, you should be able to predict beyond the time, in this case, 2 seconds. So you should be able to just plug in 5 seconds and then, the neural network will spit out something. But the moment you go beyond the area that is covered by the collocation point, the performance of the model will quickly deteriorate. So if you put in time t equals to 5 and then position x equals to say 7 meters, it'll return some value, but that value is likely, off from the ground truth. So, neural nets are inherently bad at extrapolating. Neural nets are very good at interpolating, but when it comes to extrapolation, they're not very good. So the moment you go beyond this 12 by 12 grid, from 0 to 2 seconds and then 0 to 1 meter, the moment you go beyond that regime, likely you will get a very erroneous result. Yeah, yeah. If something changes, you have to run it again. So I would view PIN as a solver as opposed to a prediction model. Solver in a sense that whenever you have a new physical condition, domain changes, parameter changes, you have to run it again. Same as the usual, direct numerical solvers, like CFD solvers, for example. If your domain changes or the Reynolds number changes or whatever changes, you have to run the simulation again, right? Same thing. When it comes to PIN, whenever something changes, you have to run it again. You have to solve it again. So that's kind of, one of the downsides. So we're gonna see, more advanced models tomorrow and then the day after tomorrow, where you can, kind of overcome that situation. So for the models that we're gonna see tomorrow, for example, will allow you to train on one condition and then use it for some other conditions. So in that way, it's gonna be more useful. But sorry. Sure. Other questions? Oh, so your question is, in the calculation of the second derivative, we calculate the time and x derivative altogether, right? And then you're asking if there's a way to avoid that calculation. Unfortunately, no. Unfortunately, no. But the additional computational time introduced by that is going to be negligible because you need to backpropagate anyways all the way to the first layer. So because of the way that the neural network is connected, neural networks are connected, even for DDX, you will need to backpropagate all the way up to the first layer. And then let me actually remove all. There you go. Thanks. So, so this is our neural network, right? And then in the first sort of derivative, what happens is we build additional computational graph. And then here's dt and dx. So that's how the auto differentiation works. Now, when you take the derivative of dx, okay, you are essentially back propagating from dx, right, all the way to t and x, right? So after back propagating from here, and then crazy thing happens in the middle, and then go over there, this is your du, d square u, dx dt. And then same thing, you go from here, go all the way up here, right? And then go over here, and that's d square u, dx square. If you look at the procedure, computing this will require the back propagation all the way up to this layer anyways. Okay? And then for the calculation of this guy over here, you just need to propagate one step to that one. And then for this one, just one step over here. So in terms of the computational cost, you have done already 9% of the calculation. And then by not doing this, you'll only save like really small negligible amount. So in that reason, I don't think PyTorch has implemented a way to selectively choose a derivative, but instead you just need to calculate everything and then ignore. That's a great question, actually. Any questions? All right. If there's no further question, I think we can wrap up for today. Yeah, 8 minutes early. So we can wrap up early today. So this is the summary of PIN. We saw several different cases of PIN and how it is used. And today we talked a lot about the limitations and things like that. So hopefully they'll give you more how do I say, some background for understanding the other method. So tomorrow we're going to introduce this thing called the neural operator, and the neural operator hopefully will resolve some of the limitations that we discussed today. And then what's even better is what's called the physics-aware recurrent convolutions. So that's my baby, and in my obviously biased opinion, that's the best method. So we're going to introduce that on Wednesday. And then on Thursday, we're going to see what's called the reduced order modeling method. So all of these neural network methods can be reduced in terms of the data size. So instead of learning the original dynamics, we can reduce the dimensionality of the dynamics and then learn from there. So we're going to introduce that technique. And then finally, we're going to be talking about the generative AI method to create some digital twin of a physical system. And then that will be the end of this week. So just a few more steps to go. You've come really far. And then PIN is probably the one that is most difficult to understand because there's automatic differentiation going on. There's this is your first time seeing neural network applied to physics applications. So probably this is the most complicated one, thing. The neural operator is also a little bit technical, but if this is clear to you, then understanding neural operator is not going to be
terribly difficult. So with that being said, if you haven't had a chance yet to play with the code, please go ahead and do it. And again, the best way to learn this topic is by doing. So you have to, break the code. You have to change things. That's the only way to learn it. Like questions like a ReLU, what do you have to use SILU instead of ReLU? Like best way to learn it is by doing it. And then, just observe how the code breaks. In that way, the knowledge will last longer in your mind and, will make more sense. So strongly encourage you to do this, even though I'm not gonna, grade it or anything. So, well, thank you so much, and I'll see you tomorrow then.